Good morning and welcome to Mathematics for Architects. My name is Neil Corse. Today I'm going to start by giving an introduction to this course and then I'll cover the first few chapters. I'll be talking about sets, symbolic logic and numbers. This is a repeat of the course from last semester. The students who took this course last semester and are repeating it don't have to attend the lectures if they don't want to. The lectures are optional. I'm going to be recording them for you even if the classroom is empty so that you can watch them back at a time of your convenience. I'm expecting to give approximately 12 classes to you, and there will be Monday mornings between 9 and 11. First, I'm going to be giving a lecture, and that will take approximately 60 minutes, although that will vary depending on the week. And then I'll be available to answer your questions in the second hour. If we don't have an hour full of questions, that's fine. We'll finish early if you want to. Typically a lecture will be 60 minutes long, but that would depend on the topics that I want to cover that week. It might be longer than 60 minutes some weeks, and it might be less than 60 minutes some weeks. We can break the material in this course up into 4 parts. Part 1 is the introduction. We'll be talking about sets, symbolic logic, numbers, and Cartesian coordinates. Hopefully that's revision for you from high school mathematics. Part 2 of this course is about the geometry of space. In part 3 we will talk about finite mathematics, and then in part 4 we will talk about calculus. And my plan is to spend 2 lectures on the introduction, 3 lectures on geometry of space, 3 lectures on finite mathematics, and then 4 lectures on calculus. There are lecture notes available for this course. You can find the link in Okan. I'm going to be examining this course with both exams and some homework. The homework will be worth 20% of the course. That will consist of 10 multiple choice tests on Okan. One extra rule I should mention: the homework is designed to help you learn the material and prepare for the exams. But if you're getting low exam scores, then homework's not helping you. So I'm using a rule which is used in most maths courses at this university. If you don't get at least 20-point average in your exams, then the homework score will be set to 0. The midterm exam will be worth 20% and the final exam will be worth 60%. I'll give more information about the exams nearer the time. If this was a classroom course, then you would have 4 hours of lectures every week, and the general expectation is that for each hour of lecture you spend an extra 1 to 2 hours outside of class. So you would be expected to study another 4 to 8 hours outside of class. So in total between 8 and 12 hours. For an online course, you're still expected to study the same amount. So still you're expected to study somewhere between 8 and 12 hours of class. 8 and 12 hours each week. Because we only have 2 hours in class, that means you should be doing another 6 to 10 hours by yourself each week. What would that be? Well, there's the homework tests. There's 10 homework tests. So almost every week you should be doing a homework test. You can rewatch the lectures. I'll make them available on both Okan and on YouTube. There's 4 lecture notes, and I'm also making my lecture slides available to you. You can read those either before the lecture or after lecture. The lecture notes have lots of problems. You should be pushing yourself to solve as many of these as you can. There's a discussion board in Okan that you can use to ask questions to me or to discuss with other students. I suggest you spend some of your time reading some maths books. I've suggested 2 good books. And you might like to watch videos by other people. For example, the mathematician calling himself Black Pen, Red Pen has some nice calculus videos on YouTube. Two good books for this course. Thomas's Calculus has both calculus and geometry in it. College Mathematics for Business, Economics, Life Science and Social Sciences, as well as those, also has nice sections on combinatorics and probability. Before I begin, let me just point out the slide number is always at the bottom left. This will tell you whereabouts we are in the lecture, and I've written the chapter title at the top if you're following along in the lecture notes. So let's make a start. Chapter 1 is about sets. A set is a collection of objects specified in such a way that we can tell whether a given object is in the collection or not in the collection. For example, these are sets. A is the set containing the numbers 1, 2, 3, 4, 5. B is the set containing apple, banana, and cherry. C is the set containing N, E, I, and L. This symbol, this looks a little bit like a letter E. This means is in the set or is a member of the set. So for example, if B is the set apple, banana, and cherry, then we can say banana is in this set, but date is not in this set. Every object in a set is called an element of the set. If we have a set without any elements, it's called the empty set. And we have a special notation for the empty set. It's this circle with a line through it. A vertical line symbol means such that. So I could write the set containing X such that X is a weekend day. So that's the set containing Saturday and Sunday, etc. Looking at a third set, the set containing all the people that are greater than 5 meters tall. Nobody in the world is more than 5 meters tall, so this is the empty set. If every element in a set A is also in a set B, then we can say that A is a subset of B. And we write it like this. A is a subset of B. So for example, the set containing 1, 2, 3 is a subset of the set containing 1, 2, 3, and 4. The bottom half of this set is an equal sign. We also allow that when we talk about subsets. The set containing Neil and Sezgin is a subset or is equal to the set containing Neil and Sezgin. The universal set is a set of all elements under consideration. We call this set U. So for example, let's suppose this rectangle is our universal set U, and let's suppose we have two subsets, A and B. The union of A and B is everything which is in A together with everything which is in B. The intersection of A and B is the things which are in both A and B. So for example, the union of A, B, and C and B, C, and D is A, B, C, and D. We take everything which is in the first set, that's A, B, and C, and also everything which is in the second set. We've already counted B and C, so we also need D. The intersection of these two sets is the things which are in both of them. A is in the first set, but not in the second set. D is in the second set, but not in the first set. We're left with B and C. The complement of a set A is everything which is not in A. So everything which is in U, but which is not in A. For example, if U is the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and A is the odd numbers in U, then the complement of A must be the set containing the even numbers in U. Our second chapter for today is about symbolic logic. A proposition is a statement which is either true or false, but not both. So for example, grass is green. That's a true proposition. 2 plus 5 is equal to 5. That's false, but because we can say it's false, it's a proposition. My name is Neil. That's a true proposition. Close the door. That's not a proposition. We can't say that close the door is true. We can't say that close the door is false. Is it cold today? That's a question. That's not a proposition. And 1. Is 1 true? Is 1 false? That doesn't mean anything. 1 is not a proposition. The symbol for or is the symbol which looks a little bit like a letter V. For example, if P is the proposition it's snowing today, and Q is the proposition it is raining today, then P or Q is the proposition it is snowing or raining today. If M is the proposition X is in the set A, and N is the proposition X is in the set B, then M or N is the proposition X is in A union B. And this is a nice way to remember these symbols. Both these symbols, one looks like little bit like a V, one looks a little bit like a U. They both open upwards. We can understand or using a truth table. P and Q, P is either true or false. That's 2 possibilities. Q is either true or false. That's 2 possibilities. 2 times 2 is 4. So we have 4 lines on our table. All the possibilities of P and Q, either true, 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 false, false, true, or false, false. And then we can write a column for P or Q. Or means at least one of these is true. So P or Q, is at least one of them true? Yes, so we write true. True or false, at least one of them is true. False or true, at least one of them is true. False or false, neither of them are true, so false or false is false. The symbol for and is this upside down V. For example, if P is the proposition I am hungry and Q is the proposition I am sleepy, then P and Q is the proposition I am hungry and sleepy. Or if X is the proposition X is in A and N is the proposition X is in B, then M and N is the proposition X is in A intersection B. And as I said before, these two symbols are connected in that they both open downwards. One looks like an upside down V, one looks like an upside down U. The truth table for and looks like this. P and Q is only true if both P and Q are true. So we can only have true if we have true and true. All of the other ones must be false. The symbol for not is this. A little bit like a minus sign, but we also have a tail on the right side. If P is the proposition your teacher likes coffee, then not P is the proposition your teacher does not like coffee. Or if M is the proposition X is greater than or equal to 7, what's the opposite of greater than or equal? The opposite is less than. So not M is the proposition X is strictly less than 7. This is a truth table for not. If P is true, then not P is false. If P is false, then not P. The opposite of P must be true. The symbol for if and only if is this double-ended double arrow. And this means P and Q are the same. So if P and Q are both true, then this is true. If P and Q are both false, then P if and only if Q is true, because they're the same. If they're different, then P if and only if Q is false. The symbol for implies is this double rightwards pointing arrow. So for example, if P is the proposition I'm in London and Q is the proposition I'm in the UK, then P implies Q, because if I'm in London, then I must also be in the UK. Let's go through the proposition and think of this example as we go through it. P implies Q means if P is Q, if P is true, then Q must be true as well. First line, yeah, that's correct. Makes sense. So true. Second line, if P is true, then we must also have that Q is true. And in the second line, we have Q is false, so P implies Q must be false. Now let's look at the bottom two lines together. If P is true, but P is not true, so there's nothing to do. We only use implies if P is true. So automatically P implies Q is true if P is false. Let's think about this in terms of the example. First line 1. If P is I'm in London, if Q is I'm in the UK. If I'm in London, then I'm in the UK. Yes, that's true. Line 2. Is it possible that I'm in London, I am not in the UK? No, so that's false. Line 3. Is it possible that I am not in London, but I am in the UK? Yes, there's lots of places in the UK which are not London. So that's okay. And line 4, I am not in London and I'm not in the UK. Yeah, that could be true. That's possible, so that's true. Before I go on, let me make a couple of remarks. We can only write P implies Q if both P and Q are propositions. So this line is nonsense. Integral from 0 to 1, 3x squared dx is equal to x cubed. Between 0 and 1 implies 1. The left part is a proposition. The part I'm underlining now is a proposition. In fact, it's a true proposition. But as I said earlier, 1 is not a proposition. So therefore, this line is nonsense. If we replace this implies symbol with an equal sign, then it becomes correct. If you mean equals, then write equals. If P and Q are propositions, then P or Q, P and Q, not P, P implies Q, and P if and only if Q are also propositions. The converse of P implies Q is Q implies P, and the contrapositive of P implies Q is not Q implies not P. So for example, if P is it is raining and Q is I get wet, then P implies Q is if it is raining, then I get wet. The converse is if I get wet, then it is raining, and the contrapositive, if I do not get wet, then it is not raining. Converse and contrapositive are not the same thing. One of these is mathematically interesting, one of them is not. There are 22 identities for symbolic logic, which I want to run through now. First few are obvious, I think. P or P. If P is true, both sides are true. If P is false, both sides are false. So these must be the same. P and P equal to P. If P is true, P and P is true. If P is false, P and P is false. So both sides are either true at the same time or they're false at the same time. So we can write equals. P or Q is the same as Q or P. P and Q is the same as Q and P. If we have three propositions, P, Q, and R, P or Q or R is the same as P or Q or R. P and Q and R is the same as P and Q and R. Doesn't matter where we put our brackets. For 7 and 8, if we have a not symbol outside a bracket, we can move it inside the bracket. But if we do that, we need to change an or to an and symbol needs to change to an or. Number 9, P and Q or R is the same as P and Q or P and R. This is similar to numbers. If we think we had A multiplied by B plus C, we know we can multiply that out to AB plus AC. Same idea for 9, and also the same idea for 10. Rule number 11, P or true. If P is true, then the left side is true or true, which must be true. If P is false, then the left side is false or true. At least one of those is true, so the whole thing is true. 12, 13, and 14 are similar. P and false. If P is true, we have true and false, which is false. If P is false, we have false and false, which is false. That's always false. P or false is the same as P, because if P is true, P or false is true. If P is false, then we have false or false, which is false. Likewise, P and true is equal to P. Number 15, P or not P. If P is true, then not P is false. So we have true or false. At least one of them is true, so that's true. If P is false, then we have false or true. At least one of them is true, so that must be true. 16 is similar. P and not P is always false, because at least one of them must be false. Not P is P. Not P is the opposite of P, and the opposite of not P must be back to P. And then for the last 5, things are a little bit more complicated. P implies Q is the same as not P or Q. P if and only if Q. This is perhaps makes more sense. That's P implies Q and Q implies P. Number 20, P and Q implies R is the same as R implies, open bracket, Q implies R, close bracket. 21, P implies Q and P implies not Q. Is it possible that P implies Q and P implies not Q? Only if P is false. So in other words, only if not P is true. And finally, number 22, P implies Q is the same as its contrapositive, not Q implies not P. That's why a contrapositive is mathematically interesting. Let's prove a couple of these. First, let's prove identity 18. That's the identity which said that P implies Q is the same as not P or Q. We need 4 rows in our truth table because P is either true or false and Q is either true or false. So we start by writing all of the possibilities. Column 3 is just a copy from the previous truth table for P implies Q. Now let's talk about the right half of the table. Not P is always the opposite of P. So if P goes true, true, false, false, then not P must be false, false, true, true. And just to make it easier for myself, I've copied the column Q across. Then using these, I can write down the column for not P or Q. Remember, for or, it's true if at least one of the two things is true. So In the first row, the third row, and the fourth row, at least one of not P and Q is true, so not P or Q must be true. In row 2, both not P and Q are false, so not P or Q must be false. Now let's look at the table as a whole. Column 3 and column 6 are the same. They're both true, false, true, true. That means these two things must be the same. P implies Q must be the same as not P or Q. And we could do the same thing for identity 22. Using a truth table, filling in everything, we can see that P implies Q, true, false, true, true is always the same as not Q implies not P, true, false, true, true. So these two things must be the same as well. And I'm going to finish this chapter by just introducing two more symbols. The symbol for all is this upside down capital A. The symbol for there exists is this backwards capital E. You can remember this because all starts with the letter A and exists starts with the letter E. And in the third chapter of today's lecture, I want to talk about numbers. What are the first numbers that children learn? The first numbers, the counting numbers, are called the natural numbers. 1, 2, 3, 4, 5, 6, etc. are the natural numbers. For example, 2 is a natural number, 7 is a natural number, but a half is not a natural number. For most people in the world, there's some disagreement for this, but for most people in the world, agree that 0 is not a natural number. And -5 is not a natural number. In the natural numbers, we can do two operations. We can do addition and we can do multiplication, and we still have a natural number. 2 plus 7, that's natural number plus natural number, is equal to 9, which is a natural number. And 2 multiplied by 7 also gives us a natural number. But we can't do subtraction in the natural numbers because sometimes if we do 2 minus 7, we don't get a natural number. So what do? How do we solve this problem? So we invent new numbers. The set Z of the natural numbers and 0 and the negative of the natural numbers is called the set of integers. In the integers, we can do addition, subtraction, and multiplication, but we can't do division. For example, 3 plus 4 is an integer, 3 minus 4 is an integer, 3 multiplied by 4 is an integer, but 3 divided by 4 is not an integer. So what do? How do we solve this problem? What did humans do in our history? We invent new numbers. Our third set is the set Q of all the fractions. More precisely, I mean all of the numbers a divided by b, where a and b are integers, and b is not 0. This is called the set of rational numbers. For example, 0 is a rational number, 1 is a rational number, 3 divided by 4 is a rational number, but pi is not a rational number. 100 divided by 13 is a rational number, but square root of 2 is not a rational number. -4 is a rational number, and 0.12345 is a rational number. In Q, in the rational numbers, we can do addition, subtraction, multiplication, and division, as long as we're divided by a number which is not 0. So are we happy now? Do we have enough numbers to be able to do mathematics? And the answer is no. Why? Why are we not happy? Because if we draw all of the rational numbers in a line, then this line has lots of holes in it. In fact, the set of rational numbers has infinitely many holes in it. So what do we do? What did humans do in our history? We invented new numbers. The set R is the set of all numbers which can be written as a decimal. These are called the real numbers. So for example, 0 is a real number, 23 over 99 is a real number, 3 over 4 is a real number, pi is a real number. 100 divided by 13 is a real number, square root of 2 is a real number. 123 divided by 99 is a real number, and 0.12345 is a real number. The real numbers are complete. That means if we draw all of the real numbers in a line, then there's no holes in the line. So we should ask ourselves, are we happy now? In other words, do we have enough numbers to be able to do mathematics? And the idea is yes. Now we're happy. Now we can move on with this course and do some mathematics. And that's the end of today's lecture. Next week, I will talk about intervals, Cartesian coordinates, functions, and sigma notation.